Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we started talking about Doppler effect, and we said Doppler effect, it is the change in the frequency when there is a relative motion between the source of the wave and, of course, the observer. And we said as long as there is a relative motion, there will always be a Doppler effect, and if there is no relative motion, there will be no Doppler effect. We've learned about the equation of Doppler effect, and we also said that the direction of the sound that is always directed towards the observer. Don't forget that. And then today we're going to continue talking about Doppler effect, and then we'll solve some of the questions that are left regarding Doppler effect. And of course, it is very important to listen or to watch this video till the very end, because there are some tips that are very important in this video. So let's both go through these questions and solve them all together. This is where we left last time, question 11. We have a question question 11 says what? It says a bat flying towards a wall emits a chirp of chirp at 140 kilohertz. Basha, is the frequency of the echo received by the bat greater than, less than, or equal to 40 kilohertz? Okay, now of course you have to think about this one here before we answer this question. What exactly happens when there is an echo here? So consider this is the wall. Okay, and here is a bat, Basha. So this bat is emitting a sound, and this bat this sound is going towards the fixed wall one, yeah? And then after it hits or strikes the wall, this sound that is going to come back or reflected one, yeah? This reflection of the sound once that is here, this is what is called an echo. All right, so this is exactly what happened, but the bat is still flying towards the wall in this case. So now, as the sound is back in here, are these two approaching one another? All right, that'll be the echo and the motion of the bat. Are these two approaching one another or not? If your answer is approaching one another, then of course the frequency of the echo that is heard or observed will be higher than the frequency of the source. Simply because we said that if the source and the observer are approaching one another, then the frequency that is heard will be higher than the frequency of the source. So this bat at the same time, right, it is emitting a sound. So this sound, that will be the source in this case. But good man, when the sound is back, of course, it is reflected back from the wall here. So now this sound is coming towards the bat while the bat is flying towards the wall. So these are approaching one another. And of course, once they're approaching, the frequency that is observed will be greater than the frequency of the source, which in this case, if the frequency of the source is 40 kilohertz, will the frequency of the observed frequency, will it be greater than the 40 hertz? The answer is yes. Don't forget, whenever it says an echo, Baba, that means the sound is reflected and now it is back. Don't forget. And by the way, because of this question, a lot of students made a mistake, because later on, hopefully this lesson or maybe the next lesson, we'll talk about the intensity as well. So there are two things you should not mix between the frequency and Babylon, the frequency of the echo and the intensity of the echo. This could be a little bit confusing here, so I'll tell you the details of that later, inshallah. So for now, good man, because the frequency of the echo, whenever it says the frequency of the echo, that means the frequency that is reflected from the wall. Of course, now it is going to be greater than 40 kilohertz. Okay, because the bat gets closer to the wall. So this too would be approaching, or the observer would be approaching, we can say the sound, or the sound is getting closer to. Okay, or these are, like approaching one another. All right, now these a few study tips, and of course you can add this two more, I believe, if you don't have it. What does it say? It says the received frequency, it is always greater than the emitted frequency when the bat moves towards the wall, Basha. Or don't forget this. But man, if the bat is continue, if this is the wall, the sound hits the wall and then comes back. So if the bat is continue to move flying towards the wall, then the observed frequency will always be greater than the frequency of the source and the one that is emitted. That is first. Second says the received frequency, it is smaller if the bat is moving away. Okay, what if the bat is kind of like emitting a chirp, and then while flying away, the sound, of course, it goes in all the directions. So one of the direction would be moving towards the wall, would be reflected. So the echo will also be moving towards the bat, but don't forget the bat will be moving away. In that case, of course, the bat will be, because it is moving away, so the frequency that is heard will be less than frequency of the source, because you can say they are moving away from one another. Okay, now third point here, it says the received frequency, it is the same as the emitted if the bat is at rest. If the bat is not moving, of course, then a chirp, it is emitted, then it hits the wall, then it is back. If the bat is at rest, then of course the bat will hear the same frequency, don't forget. Okay, and this is the question that we were talking about last time. It is related to the fire engine, and we've solved this one too. And we said how we can solve that. Now we have a few questions regarding Doppler effect. These questions are very important. So let's solve each one of these together. Okay, so the first thing that we have, it says we have a police or parked ambulance. Basha, we have a parked ambulance. Basha, it's emitting its sound. Okay, or it emits a sound of frequency of this much. Let's just prepare this. Okay. We have the speed of sound, which is this much as well. Just keep that here. Okay, now we have a parked ambulance emits the sound of frequency on this. So this is the frequency of the source. We can say it is 1200 hertz. Basha. And then what is the frequency detected by an observer inside another car? But don't forget, when it says a parked ambulance, that means the velocity of the source, it is 0. So let's just start with the velocity. Velocity of the source is 0. Frequency of the source, that is 1200 hertz. Okay, and then frequency detected, what is the observed frequency, that is unknown, by an observer inside another car moving with a velocity of 20 meter. So this velocity of the observer, it is going to be 20 meter, but first, if it is moving towards the ambulance. So here's the ambulance, okay, and here's the car that is moving. So the sound or the ambulance, it is, remember, it is parked, so the velocity of the source is 0, and this is the direction of, we can say the direction of the sound. Don't forget, we said it's always towards the observer. And this is the velocity of the observer, which is 20 meter per second first if it is moving towards the ambulance. Basha, remember the main equation that we have, Basha? We said frequency that is observed, it is equal to what? V minus V observer, right? V minus V source. These are all in bracket. Okay, and then multiply by the frequency of the source. We can write it here at this point here. Alabama. Now, before that, let's just plug in the signs in here. So remember this, that would be the direction of the sound. So the velocity of the observer or the source here, this velocity is 0 because it tells you the ambulance is at rest or parked. Basha, this velocity is moving towards the ambulance. Are these two same direction or opposite direction? Good man, this is the key. We always compare that with the direction of the sound, don't forget. So these are opposite. Opposite means negative, right? So now V observer is negative. Now you have to write a negative inside this bracket here. So negative, negative later, of course, is going to be positive. So let's just keep it or write it down. So 1200, that is the frequency of the source. By the way, speed of sound, that is 340. So here's 340 up and 340 down. Okay, good man. This is negative, negative becomes positive. What is the velocity? 20. And then we can say minus 0. Even if you don't write that, of course, this is not going to change anything at all. So what is the observed frequency now? Observed frequency is going to be 1270.4, if I'm not mistaken. Right? So that is, yes, 1270.6 actually, hertz. Basha? 0.6 hertz. This is the observed frequency when the car is moving towards the ambulance. Now, that is for part A, Basha. Now, part B here, all right, for part B, it says this time, if the car is moving away from the ambulance, now we're going to change the direction here. If the car is moving away from the ambulance, so now this is going to be the direction, Basha. Okay, once again, so frequency that is observed, frequency of the source, V minus V observer, V minus V source. These are in bracket, all right? So now let's write it down, 1200 again, times 340, right? Both up and down. And then once again, if it is moving away from the ambulance, these are same direction one, yeah? So this is going to be positive. But positive, negative, it is going to be negative 20 here. And then minus, or you can say divided by 340 minus 0 because the ambulance is parked or the source is parked. So now if you do the math, of course, the frequency that is observed, it is equal to what? It is equal to 1129.4, 29.4 3.4 hertz. So this will be the difference in the observed frequency once if the car is moving towards the ambulance, and the second part it is moving away from the ambulance. And once again, we'll compare the direction of the motion for both the source and the observer with the direction of the sound, which is always towards the observer. We can finalize the signs whether it becomes positive or negative there. All right, by the way, this question is totally fine if they gave you, for example, the speed of the ambulance too. Then in that case, of course, we could have just write the velocity there depending on the direction that is given. That'll be this simple regarding this one. Basha? Okay, now let's go to another question here. The next question that we have, what does it say? It says, a police car moves at a speed of 90 km per hour and emits a siren of frequency 1000 hertz. What is the frequency of the sound detected by a standing observer? Okay, now I need you to know. Okay, so this is the speed of the source, Basha. This we can say V of the source. Okay, and then standing observer, that means V observer, it is going to be what? It is going to be 0 because it is standing. So no velocity. It says, and also remember says, that by a standing observer as the police car approaches here. What does approaches mean here? That means moving or getting closer. And speed of sound in air, it is 340. Okay, so let's do this one again. All right. So, but first of all, you have to do some conversions here. Let's rewrite the informations given here. So the first thing says police car moves at a speed of this one, this V source. Don't forget, this is 90 km per hour. Okay, you have to convert this one to meter per second. How can you do that? You could just simply divide by 3.6, and then you can convert from kilometer per hour to meter per second, Basha. And if you did not do this, we know that every kilo is 1,000, right? Every hour is 3,600. So once you divide the two, you get exactly the same thing. But you either multiply by 1,000, divide by 3,600, or you simply just divide by 3.6, and then of course you get the same answer. So you choose one of them, whichever you think it is the easiest for you. That'll be totally fine. So what would be the answer in this case here? Just move this one upward a little or scroll it up. So it is going to be 25 meter per second. So the velocity now, velocity of the source, by the way, 25 meter per second. That is the first thing. Now let's go back to the second part of the question. Says emits a siren of frequency. Got that now? The frequency of the source, it is 1000 hertz. Basha? It says, what is the frequency of the sound detected by a standing observer? So the frequency that is observed, F prime, it is unknown here. And then it says by standing observer, that means the velocity of the observer is what? It is 0. Okay, and then as it is approaching here, the speed of car, so velocity of sound in air, it is 340 there. Now let's draw the diagram here. So this is the police car. Okay, here's a police car that is approaching a standing observer. Here is the observer that is standing, Basha. Emits the sound and all that. So the direction of the sound that is going to be towards the observer, as you can tell here. Basha. Now let's write the equation here. Gutman frequency or F prime, dakata F, frequency of the source, times what? Times V, Gutman minus V observer, V minus V source. And these are inside brackets, don't forget them. All right, one more time. So this is 1000, right, times speed of sound in air, it is 340, 340. Now regarding this one, Baba, it says the police car approaches the observer. That means the velocity of the source, right, it is moving the same direction as the sound here. So this is going to be positive, right? But now, write this positive inside a bracket. Positive, negative, of course, is going to be what? Sorry, my bad. I should have done it below here. All right, this is for the observer, though. All right, good. Now, velocity of the source, because it is approaching the observer, velocity of the observer is 0 there. Don't forget, because it's standing. Kata gutman direction, okay, direction, okay, it becomes positive here, but draw or write this positive here. Positive, negative, it becomes negative. Now, what is the speed of the police car? We said 25, we converted that. And then speed of the observer is 0 because it is standing or stationary there. Now, all you have to do, just multiply and then do the math. You'll be getting the frequency that is observed. And what is that equal to? It is equal to 1079.4. 1079.4 hertz. That is the frequency that is observed by a standing observer. All right. These questions are easy, actually. Now, can we reverse this question? Absolutely yes. All right. How can we do that? We can, if we have the observed frequency, we can find the velocity of the police car, and then we could have converted that into kilometer per hour as well. All right. So always remember, these questions can be reversed. Imagine or consider, if the frequency of the source is 1000 Basha, the frequency that is observed, all right, it is let's just say 1079. Let's just assume that 0.4 hertz Basha. This is the observed frequency. And then let's consider that the speed of the source it is 25, and then the speed of the observer standing, that would be 0. The question, actually this one would be unknown here. What is the speed of the source if they gave you this question? And by the way, if the question, don't expect the question to tell you if two frequencies are given, like the emitted frequency or the frequency of the source and the frequency that is observed. Once these two are given, don't expect the question to tell you whether the car is approaching or moving away. Because once you compare the two frequencies, you can always tell if it is getting closer or moving away. Watch this. Now, if we compare these two frequencies, Basha, the frequency that is observed, obviously it is higher than the frequency of the source. Yes or no? Basha, let's cut frequency. The observed frequency will be higher than the frequency of the source. Then halakati, when they're approaching here. So always remember this, or use this as a key for yourself. In case if they didn't tell you the car is moving closer or moving away, if you have these two frequencies, you can always tell whether if it is moving closer or moving away. Again, if the frequency that is observed, watch this, if it was less than 1000, let's say 850, for example, Basha, if the frequency that is observed is less than the frequency of the source, then you can clearly see that the object is moving away. So if it is approaching the frequency that is here, it will be higher. If it is moving away, the frequency that is here and observed will be lower than the frequency of the source. All right, now, so if that is the question here, can we find the speed of the question? Again, does not tell you whether if it is moving closer or away. How can we tell, Gutman, based on this? Yalla, find the speed of the police car at this point here. Okay, so Gutman, so this is the police car. Okay, and here's a standing observer. Gutman, because the frequency that is observed, of course, it is higher than the frequency of the source kata, they must be, or the police car must be approaching from this. So this would be the direction of the sound here, and this is the observer there. Now frequency and f prime the kata f, frequency of the source, Basha, times v minus v observer, which is stationary, v minus v source, which is moving. We can say closer to this. This frequency, Gutman, is 79.4. This one is 1000, Basha. And then v, that is, of course, 340. Gutman, velocity of the observer is 0, so that would be 0 over 340. Gutman, regarding the direction, Baba, these two are same direction, even if they don't tell you, because you know the frequency that is observed will be greater. Kata, it is approaching. If it is approaching any same direction, Baba, same direction, any positive, but bring this positive here, positive, negative, it is going to be negative v of the source in there. Now, all you have to do is just cross multiply. First of all, divide both sides by 1000. Right, these two cancel out. And then after that, once you do this, you could just multiply. So let's just do the whole thing now. Let's say 1079. Okay, 1079.4 divided by, could be any number, by the way. That is divided by 1000. It is equal to 1.079. 1.079. There's a 4 as well, but we'll just keep that. Actually, let's just do that. Here it is 340 divided by 340 minus v source. All right, now all you have to do just continue, or you can use cross multiplication one, yeah. So in this case, is going to be 340 times 1. It is equal to 1.0794 times what? Times 340 minus v source. And once again, you can see that you can again divide both sides by 1 point this much, so that we can get this one here. Divide both sides by 1.0794. 0.0794, and then this one too. These two cancel out. So what is, let's see, what is this equal to? 340 divided by 1.0794. The answer is equal to 314, about 315 actually. 315, it is equal to 340 minus V source. Now all you have to do, how can you find the velocity of the source now? Just move this one to the side and move this one there. So what would be the answer now? We'll say V source, velocity of the source, it is equal to 340 minus 315 here. So what is it equal to? That is going to be 1525, yeah? So V source, it is equal to 25 meter per second there. And then, but this is in meter per second. How do we convert meter per second to kilometer per hour? If you want to change kilometer per hour to meter per second, we've divided by 3, yeah? We've divided by what? We've divided by this kilometer per hour. We've divided by 3.6, yeah? The answer was this much meter per second. But can we do the reverse? If I have meter per second, how can I convert this to kilometer per hour? We'll say whatever the answer is, just multiply by 3.6 in this case. That'll be the opposite of this. Then multiply by 3.6, then you'll get the answer in kilometer per hour, Basha. So whatever the answer is going to be kilometer per hour. If we have 25 meter per second, how do we convert that to kilometer per hour? So 25 times, this time remember, times, not divide, times 3.6. The answer is going to be again 25 times 3.6. The answer, okay. The answer will be 90. 90 what? 90 kilometer per hour. So this is the reverse of this question right here. Okay, now the next question is very interesting. So let's do the next one here. All right. Might just erase this one. All right. Now, here is this question actually. And there's a very interesting question regarding this one too. Now, I want you to focus at this question here. What does it say? It says a Formula 1 car moves away from a fixed observer who hears the sound of its engine, sound of its engine with a 20% reduction here. So a Formula 1 car moves away. That's one of the keywords. From a fixed observer. That is the second keyword we can say. The observer is fixed. That means velocity of the observer, it is 0. Okay? Who hears the sound of its engine with a 20% reduction, but reduction of what? Of its original frequency. That is another keyword. The question says, what is the speed of the car? Remember, 20% reduction. What does it mean? That means it is going to be, or the sound that is here is going to be 80%. But let's talk about this one. And don't forget, speed of sound in air, it is 340 meter per second. So once again, there is a standing observer here, okay? Now there's this Formula 1 car, but this Formula 1 car, it is moving away. Basha, it is moving away from a fixed observer. But the direction of the sound, we know that it is always directed towards the observer, right? So that would be the direction of the sound. So the speed of the Formula 1 car, speed of the source, it is unknown. We're required to find this one here, Basha. And then this observer, it is at rest. Basha. So now let's begin with the equation that we have. The equation, or the frequency of the observed bubble and the observed frequency, or something before that. It is moving away, Basha. This person, the observer, hears a frequency with a 20% reduction of the original frequency. What does this exactly mean here? That means whatever the frequency of this engine here, or this sound here, this guy will hear 20% less than the original sound in here. Basha, so now, let me give you an example here. You go to a store, you want to buy something. It says the cost of this thing, it is $100, but now we have a 20% reduction, Basha, or 20% discount. Basha, if something, like if something's, let's say, has a price tag, let's say of 100, but $100, or 100,000 Iraqi dinar. But then the owner or the, like the guy there says there's a 20% discount, Basha, of course, of the total. So now how much do you have to pay now? You have to pay 80% of the total. Do you agree? Yes. So now go back to this question. The question says this guy hears 20% less than the original sound. Basha, if he hears 20% less than the original sound, then how much of a sound does he hear? He is hearing 80% of the sound here. So once again, Basha, this observer, okay, or the frequency that is observed, of course, you can say that it is 20%, Basha, less, Basha, less than the frequency, Babylon, or the frequency of the source, Basha, frequency of the source. Kata, how much does he hear? We can say that the frequency that is heard by the observer, if it is 20% less, Baba, we can say he hears 80% of the total, Basha. Kata, he hears or they hear 80% of the total sound. And that is what it means, 20% reduction. If not, of course, you can say 100% minus 20. That is also fine. Like this is the equation. By the way, let's not forget this actually. 80% of what? 80% of the frequency of the engine. Don't forget. Basha, if you don't want to use this, you can say the frequency that is observed. Basha, the kata tsibaba, the kata 100% of the Babylon of the original sound, because we have 100% minus 20% of the frequency of the sound. These are percentage, so let's keep them as a percentage, Basha. The total frequency of the sound, that is 100%, Basha, minus 20% of the frequency of the sound, Kata. If 20% is less than 100, Kata, how much percentage will they hear? It is, or they're going to hear 80% of the total, but of the frequency of the sound. So, but I don't think you need this much here. Just remember, if 20% less, yani, they're hearing 80% of the original frequency and the frequency of the source. Now let's go back to the equation of Doppler effect. Now frequency, where f prime, the kata tsibaba, got the frequency of the source, v minus, that would be speed of sound, v minus speed of, or velocity of the observer, v minus Babylon speed of the Formula 1 here, the source. But Gutman, this is the observed frequency. When Gutman, the observed frequency is 80% of the original sound. Basha, 80%. Can I write 80% this way? 80%, yani 80 over 100 of the original frequency. Yes or no? Basha, 80%. Isn't it also equal to 0.802? Yes, that is what it means of the original frequency. By the way, because the frequency is not given, so this is 80% of the frequency of the sound. This is our frequency of the source, Basha, and this is going to be frequency of the source, so this two will cancel out, but we'll just give it a second. So this is 340, Basha. And now the observer, good mind, it is stationary, so it's going to be minus 0. Even if you don't write that, that is totally fine. But look, if the Formula 1 car is moving away, so this will be the direction, yes or no? Now compare the direction of the source with the direction of the sound. Are these the same direction or opposite direction? Opposite. So if it is opposite, the direction of the speed, Yan Babylon velocity is going to be negative. Now bring this negative, write it here. Negative, negative, it becomes positive. Positive chair, v of the source. Now all you have to do, just find the velocity of the source there. This two cancels out, don't forget, Basha. Now all you have to do, just cross multiply, and that'll be it. So 0.8 or 80, doesn't matter. It is equal to 340, Basha, divided by 340 plus v source. Now, once again, let's use cross multiplication. That'll be 340 times 1, 0.8 times 340 plus v source. Now, you could divide both sides by 0.8 and 0.8 in here. This two cancels out. So 340 divided by 0.8, it is going to be 380 or 400 something. 340 divided by 0.8, it is 425. So this is going to be 425. It is equal to 340 plus v source. Okay, now all you have to do, just move this one to the other side and you can find v of the source. So velocity of the source, the kata 425 minus 340. Okay, now Do the math and see what it is. 425 divided by 3, minus 340. The answer is going to be, or it is equal to 85. So velocity of the source, it is equal to 85 meter per second. But because it is a Formula One car and these are moving fast, so more likely you will be asked to convert this in to kilometer per hour, or more likely the options will be given in kilometer per hour. So how do we convert meter per second to kilometer per hour? All you have to do just multiply by 3.6, and that is going to be in kilometer per hour. So let's see, what is it in kilometer per hour? So we'll say 85 times 3.6. So the answer is going to be 306 kilometer per hour. This is how fast the Formula One car is moving away from the observer. Basha, what if in this question, the question did not say the Formula One car is moving away? Could have you, for example, tell that the Formula One car is moving away still? Yes. But madam, or as long as there is a reduction, that means that it must be moving away. What if the Formula One car is moving closer, moving towards the observer? Okay, the frequency that is observed would have been more than the frequency of the source, and that is going to be, we can say, the first thing that they can change regarding this question. If everything is the same situation given, the Formula One car is moving, Babylon, let's say, or the observer hears a frequency with a 20% reduction of the original, and of the frequency of the sound, we can say, what if the person hears, or the observer hears a frequency with a 20% increase than the original or the frequency of the sound, Basha? So we could have, of course, what would have you done here in that case? So let's go back to the question and change this one, Basha. We're given exactly the same situation or same everything here, Basha. But the question says, what if the question, once again, it does not mention, let's change a few things here, Basha. This time the question does not tell you it is moving away. That's one thing they might not mention. Fixed observer, that'll be mentioned, Basha. So velocity of the observer is 0. Who hears a sound of his engine with 20% increase this time, Basha? Increase. If the question says with the 20% increase of its original frequency, what would be the speed of the sound? So now let's analyze this one here. Basha, in order to find the direction, you need to know whether the Formula One car is approaching or moving away. Because we said as long as, or because the frequency that is observed, it is 20% increase than the original, that is higher than the frequency of the original or the sound, then they must be moving towards, or you can say the Formula One must be moving closer. So now, Gutman, this is the observed or the observer here, and this is the car or the Formula One car, whatever. Okay, here. Now, because this time, if it says here is with a 20% increase, if the frequency is that is observed 20% more than the frequency of the source, this only happens when there is an approach. So this is stationary. Obviously, this is not moving. So it has to be getting, or the Formula One car must be getting closer to the observer. We're going to do exactly the same thing here. But now the frequency, let's write it here. The frequency that is observed, that is going to be 20%, Basha, more than the frequency of the source now. Basha, if we consider this, good, now frequency of the source, if we assume it is 100, now 20% more, so the total is going to be 120. But if you prefer numbers, for example, we said this is 100% of the frequency of the source. Now there is 20% more, Basha, 20% more than, Basha, more than the frequency of the source in this case, Basha, with the 20% more. We can say that the frequency that is observed is equal to 120%, don't forget, of the frequency of the source in there. So I got Louis Basha Baba. So now how do we put this into calculations? Well, first of all, you can convert this 120% into a decimal, we can say. 100% divided by this, that is going to be 1.2, Basha, 1.2 times the frequency of the source. Now, we can use the Doppler effect equation, Baba. Frequency or observed frequency equal to frequency of the source, V minus V observer, V minus V source. These are in bracket. Okay, good man. Nestack Baba. Legati frequency observer ke Babylon. Then we'll put 1.2 times frequency of the source. Frequency of the source there. This is 340 minus 0 because the observer is at rest or stationary, and then 340. If it is moving closer, let's go back to the direction here. If it is approaching, the direction of the velocity of the source is going to be the same as this, right? So this is positive, but bring the positive right into the equation here. Positive, negative, that would be negative velocity of the source. Now all you have to do, just do the math one, yeah? So these two cancel out. 1.2, that is equal to 340 minus V of the source. All right, so once again, use cross multiplication. 340, that is equal to 1.2, 340 minus V source. Divide both sides by 1.2, 1.2. This two cancels out. So 340 divided by 1.2. 340 divided by 1.2, the answer is going to be 283.33. 283.33. It is equal to 340 minus V source. Basha, now all you have to do, just find V source one, yeah? We can move this one, right, to the right in here and bring this one to this place. Kata V of the source, the kata se 340 minus 200, 283.33 one, yeah? So what is that equal to? 340 minus 283.33. The answer is going to be equal to 56.67. So V source, the kata, 56.67. This is in meter per second. This is how fast the Formula 1 car would be approaching the observer. But if you want to find this velocity in kilometer, we could just multiply this one by 3.61, yeah? 56.67 times 3.6, then of course you can find out the velocity in kilometer. So 56.67 times 3.6, the answer is going to be 204, right? 0.0 something, 204 kilometers per hour. This is how fast the Formula 1 car would be moving by getting closer from the observer. That is one of the things that they can change regarding this question. Asha, there's also another question actually that we can change regarding this question right here. And what is another way that they can change this question, Basha? But watch this carefully. Now, the same Formula 1 car, Basha, it is moving this time, moving away from a fixed observer. Basha, a Formula 1 car. This Formula 1 car, it is moving away from a fixed observer. Watch this. Now, I'll show you a question 2 here. It is moving away. This Formula 1 car, it is moving away from a fixed observer. Basha. But this time, this fixed observer, so velocity of the observer is 0. But this time, they might give you the velocity of this one here. So let's say the velocity of this Formula 1 car, it is, let's just assume that it is 250 meter per second. We can actually convert that to kilometer per hour. Let's say it is about 300, or maybe let's just make it 285 kilometer per hour. This is how fast it's moving away. So the question would be asking, how much percent of the frequency, or you can say how much percent is less the frequency of the observed, Babylon, the observed frequency compared to the original sound. I'll repeat the question. This is the same situation. The observer is at rest. The Formula 1 car is moving with this speed away from an observer. What is the percentage, Basha, of the frequency that is observed compared to the frequency of the source in here? بمعنى it is the reverse of this question here. If this أقرأ Formula 1 car, if it is moving away, صدات سندي كم تر بابلن أو جري and this observer صدات سندي كم تري أو frequency جل دبي صدات سندي كم تر ل frequency source. Okay, I hope you got my point in here. The frequency that is observed by this observer, how much is Babylon, how much is less compared to the frequency, how much percentage is less compared to the frequency of the source in there. Basha. So once again, they will give you the speed of sound in air, which is 340. Basha. This is the speed of sound in air. The next thing, you will have to do that yourself. So how do we do this question here? Now, this is frequency that is observed. It is equal to frequency of the source, V minus V observer, V minus V source. This is what you need to know. And yeah, got the frequency that is observed, but the kata this, right, times that. So now this frequency, it is unknown here. So this is 340, 340. The observer is at rest, so this is 0. If it is moving away, so the direction of the source is going to be opposite to the direction of sound because it is always towards the observer. Kata would be negative. Velocity of the source is negative, Basha, but bring this negative here. Negative becomes positive. So positive, the speed of the source. But don't forget, this is given in kilometer per hour. So how do we convert this to meter per second? All we have to do just divide by 3.61. Yeah, kata V source, the kata 285 divided by 3.6. Let's see what is this equal to. 285 divided by 3.6. The answer is going to be 79.16. Basha, 79.166.16. Let's round it up and make it 7. This is meter per second. This is how fast it is moving away in meter per second. So write it down. 79. Okay, 79 what? 1.67 there. Now, all you have to do is just do this math in here because this frequency is unknown. Let's see what is that equal to here. Basha, 340 minus 0, you can ignore the 0, divided by this 2 combined here. So let's see what is this equal to. 340, Basha, divided by 340 plus 79.167. Basha, the answer is going to be 0.811. So we can say the frequency that is observed, it is equal to 0.811, Basha, 1 of the frequency of the source in here. So I need you to be careful right here. Kata, because this Formula 1 car is moving away, so it is obvious the frequency that is observed is less than 1. That's pretty normal and it's convenient, and I believe everybody needs to know this. If it was getting closer, this number should have been bigger than 1. That is obvious, right? But now, this frequency that is observed, how much is of the total now? You can multiply this by the 100 to get a percentage, right? So we can say multiply by 100, or the percentage here, the frequency that is observed, if you multiply this by 100, it is going to be 81.1% of the frequency of the source. The frequency that is here, it is 81.1% of the frequency of the source. But that is not the answer of the question. What percentage, the one that is here, what percentage is less than the total here? Baba, this is the one that is here, Basha, just like the discount. This is how much, let's say, you paid, Basha. But how much, for example, is less than the total price, and how much is less than compared to the original frequency? Basha, agar hashta point Babylon, if the person hears 81.1%, Basha, how much is less compared to the total? We could just say, now 100% minus 81.1%, what would be the reduction, or how much is less here compared to the total, or compared to the sound frequency of the engine, or the frequency of the engine or the car, whatever. So we'll say 100 minus now 81.1. So the answer is going to be 18.9. Basha, the frequency that is observed, Basha, it is 18.9% less, Basha, less than the frequency of the source, Basha. Kata, Remember this, Baba, this is the percentage you find, but the percentage you find, this is the frequency that is heard, that is observed, Basha. Basha, أو عندي كم ترى لا frequency total, okay, it is 18.9% less, Basha. So be aware of this kind of ideas as well. And whenever you solve a question, make sure you always reverse the question and see how it ended up. Sometimes you'll be surprised how good the idea will be. Let's move on to another question. This question is also one of the most important questions that we have, Bashababa. So we're going to continue in a second. All right, what does it say? Now it says a bat flies towards a fixed wall and sends a sound of, or an ultrasound of frequency 80 kilohertz, and here's the reflected wave with a frequency of 90 kilohertz. So there's a bat that is flying towards a wall, Basha. It emits a frequency of 80 kilohertz, Basha. And then here's an echo, which is a 90 kilohertz. If a bat is moving towards a wall, the echo that hears, of course, it is going to be the frequency of the echo. It is going to be higher than the frequency of the source. Why? Because they're approaching one another. The reflected sound is moving towards the wall, Basha, and directed towards the wall. The bat is moving towards the wall still, so these two are approaching one another. So the frequency that is heard, Basha, which in this case will be the frequency of the echo, will be higher than the frequency of the sound, or the source in this case here. Also, don't forget, the first question says, give the expression of the apparent frequency of this wave when it strikes the wall here. Only when it strikes the wall. Now, at this point here, I need you to write this for me here. The expression, Baba, it means write the equation, Basha. Write the equation of this apparent frequency and the observed frequency of this wave when it is, or when it strikes the wall. Basha, did you write that? All right, now the next thing, let's solve this one together. So we have a wall, Basha. So here's a wall. And the bat is moving towards the wall, or flying towards the wall here. Let's consider this is the bat, Basha. My drawing are perfect, so no complaints. All right, so it is moving or flying towards the wall, Basha. This is the, we can say this is the direction of a sound, Basha. It is moving towards the wall at this point here. The bat is flying towards the wall, so the direction of the source is also moving towards the wall. Basha, the question says, what is the expression of this sound when it strikes the wall? Not when it's coming back, only when it strikes the wall here. Basha, because the sound is moving towards the wall, can I consider the wall, can I say the wall is the same as an observer that is at rest? Yes, because the wall does not move, right? So at this point here, I'll consider the wall the same as an observed, or an observer who is at rest. Why? Because the question itself tells you that the sound is moving towards the wall. So the wall now is the same as an observer here. Basha, what will happen to the equation now? Let's say the equation, the question only wants the equation, by the way, no numbers, no nothing. Let's say the frequency that is observed, I got the frequency source, okay? V minus V observer, Basha, V minus V source. But this is not finalized yet, Basha. Got the frequency that is observed, I got the frequency source, okay? Basha, V, that would be speed of sound in air. Gutman, the observer here is 0, it is at rest, so that is just going to be V. And then divided by V again, Basha. These two are the same direction, Wanya. This velocity of the source has a positive sign, Wanya, because these two same direction. Basha, write the positive here. Positive negative becomes what? Becomes negative V of the source. And that is the equation that you need to know. That is what the question is asking for, and this Benin Wazari too, this expression right here. Now, that is the first part of the question. The second part says, what is the, where does the sound, what is the sound of the wave, or what is the source of the sound of the wave when it's coming back? Basha, now we know that once this sound hits the wall, of course, it is going to be reflected, yes? So I'll just draw it below here so that we don't mix the diagram here. That is the same sound here. instead of writing it here that is reflected or coming back, I'll just draw it below here. Doesn't make any difference now. Now, once it strikes the wall here, this is going to be reflected, yes? This is the reflected sound, and the reflected sound, we can call it echo, yes? And you agree. So now, but where does this sound is coming from? Isn't it coming from the wall now? It's not like coming from the wall, but it is reflected from the wall. So can I consider the wall as a source? Absolutely, yes. So if the question about a source, and it is the place where the sound is coming from. So no, it doesn't matter where or which object does it come from. If it comes from this way here, from the wall, so we can consider the wall as a source. We know that this, of course, it is reflected from the wall. It is the bat sound one, yeah? But because it is reflected and it's coming from the wall, so now we consider the wall as a source. As a what? As a source now. The same as if it comes from or the wall here. Basha, that'll be the second part of the question. Kata, what is the source of the sound on the way back or of the echo? That is going to be the wall. What about part 3 here? So here it says, what is the emitting source of the ultrasound wave on the way back, Baba? It says on the way back, and when the sound is returning here, like from where does it exactly come back? Isn't it reflected by the wall here? Kata, it is coming from the wall. So in this case, the wall, it is considered the same as a source now. Now, third point, or part C, it is the most important one. It says determine the flying speed of the bat. Determine what? The flying speed of the bat. Now, at this point, you really have to be careful. Now, let's do this one together too. So, one more time. Let's clean this and do this one more time, Basha. So here we have, this is a wall, Basha. Mom, this is the bat. How about it? Let's see if we can draw a nice rectangle bat. Okay, I think that is all right. Let's rotate this. Okay. Wait. So this is a bat we can consider, Basha. So good mom, this bat, it is emitting a sound of 80 kilohertz. So this sound is now, this will be the direction of a sound. Don't forget, it is towards the wall. You agree, I guess, one, yeah? Now, we could, of course, draw a line here. We can say this is for the sound, or bat as a source in here. Basha? Bat as a source. Wow. Yalla Baba. Now, Gutman, after that, what happens when this sound strikes the wall? Of course, the sound comes back in here, or the sound will be reflected. Once again, I'm not going to draw here. I'll just draw below here. This would be the sound that one is coming back, but the bat is still flying towards the bat is still flying towards the wall. Masha? The bat is still flying towards the wall in here. So this is the direction of the bat in there. But watch this. Here, who's making or emitting the sound? It's the bat, right? So now bat here, okay, it is the source at this point. So that we can say the source, V of the source. Basha, why the source? Because this sound is coming from the bat. So the bat is the source. But while the sound is coming back in here, so this would be the sound, or this is the echo. Now, the bat is flying, but who's going to hear this echo? Basha? The bat is going to hear the echo, right? So now, because the bat is hearing the echo, this time here, the bat is the observer. Observer, Basha. So now we can say V observer. I hope this is obvious now. I'll repeat this one more time. Gotmanera, the bat is flying towards the wall and also emits a sound. Basha of 80 kilohertz. Wazha. So, but who's emitting the sound? That is the bat. So here, the bat is the source and also moving or flying towards the wall in here. Okay, now, after, for example, this wave, it is going towards the wall. Now this wave hits the wall, and then it is reflected, yes? Now, as it is reflected here, this sound that is moving towards the bat again, who's going to hear the reflected sound, which we call it the echo? The bat is hearing the sound one, yeah? Kawata, this time the bat is the observer. So at the same time, watch this, Baba. Whenever bats are mentioned, they are the source and the observer at the same time. Don't forget, because this sound will be going and coming back and the bat will hear that. Basha, now how do we write the equation for this? Now watch this. Now frequency of the observer, they got the frequency of the source, speed of sound in air minus speed of the observer, right? Speed of sound in air minus speed of the source. These are in bracket, don't forget. Basha, now let's finalize these equations maybe first. So here, Gutman, the first part, who's the source? The bat is the source, because the sound is coming from the bat as a source. Basha, and the bat, because it's flying towards the wall, so the direction of the sound is towards the wall as well. Kata, these two are the same direction. If it's the same direction, Kata, V of the source is going to be positive. Positive, actually, Baba. But dua will be positive, negative will be negative. We'll deal with that later, Basha. Now, when this sound strikes the wall and then it is reflected, so we have an echo, right? So, but now this sound, that is, who's going to hear the sound? That is the bat itself. But at the same time, the bat keeps flying towards the wall. When, yeah, yes. But the echo is in the bubble. Now this is the direction of the sound. Now it is moving towards the bat. Are these two the direction of the sound, which is the echo now, and the direction of the bat flying as an observer? Is this the same direction, opposite direction? Opposite. Kata V of observer here, it becomes what? It becomes negative. So write a negative here. Now let's finalize this two together. Katman, the observed frequency, it is 90 kilohertz. Masha? Now the frequency of the source, it is 80 kilohertz. Now you might say, why didn't you convert the kilo, Baba? Because I have kilo here and there. I can just cancel them out, so I don't have to convert that to hertz. Because you can do that too. That would be 90,000 and 80,000. They still cancel with one another out. Basha, multiplied by speed of sound in air, 340, right? 340. Basha, and then later minus Baba, the beta, positive. But Gutman, who's the observer? The bat is of the observer. So this is speed of the bat. Lakhwari, positive, negative, the beta negative. When once again, who's the source? That is the bat, who's the source. Kata bat, or we can say these speeds for both the observer and the source, these are for both, or you can say both are for the bat. Allah Baba, kilohertz cancel out with kilohertz. The 0 with this one here. So we can say 9/8, divide both sides by 8, it is equal to 340 plus V bat, Basha, Lakhwarish 340 minus V bat. All right, now let's cross, actually before we cross multiply, so let's just divide 9 by 8. 9 divided by 8, it is equal to 1.125, because it makes it easier. 1.125, it is equal to 340 plus V bat, Masha, divided by 340 minus V bat. Yalla Baba, can we cross multiply now? Yes, let's do that. So this 340 plus V bat times 1, nothing changed one, yeah? It is equal to 1.125 times, there is a plus in between, so you have to use a bracket now. 340 minus V bat. Now you know what to do next one, yeah? We multiply this into the bracket here. So once again, let's just rewrite this one. 340 plus V bat, Masha, Dakata. Let's see what is this equal to. 1.25 times 340. The answer is equal to 382.5. 82.5 minus 1.125 V bat. Yalla Baba, V bat and V bat at one side of the equation. The numbers at one side too here. Later we have 1.1. There is 1 V bat. That is going to be a total of 2.125 V bat. Basha? Because there's 1 V bat. This is negative. If it comes to this side, it becomes positive. That is going to be 2.125. Wajda tita la akidi kebaba. got the 382.5 minus 340. Now 382.5 minus 340 دكاتة cent, it is equal to 42.5. Kata, let's rewrite this. 125 VBAT دكاتة 42.5. Okay, now how do you find VBAT now? Let's say VBAT, or both sides divide by 2.125. When ليش 2.125. So these two cancel out. Kata VBAT دكاتة 42.5 divided by 2.125. The answer is equal to 20 meters per second. This is how fast the bat is flying towards the wall. And because this speed is not that much, well, actually, it's big enough. So it's totally fine if they gave you this in the options in kilometer per hour, even though I don't think so. But just in case, Annie, if they ask you to convert this to kilometer per hour, you know what to do. And you just multiply by 3.6, and then you'll find the velocity of the bat in kilometer per hour. I hope you understand. I hope you understood how it is done, Baba. Remember, let's go back to this. But man, first, remember this. As the bat is approaching, Asha, so this case, the bat will be the source. And then as is coming back, or the sound is coming back, the bat will be the observer. Basha, let's generate a QR code here. If you want to have this one, Basha, as a picture, of course you can have it. All you have to do, just if you're using a cell phone, Baba, you could just, of course, scan this code right here. And then these are so many pages actually for all of this. We could just do that for one page, but if you scan this one, whatever I wrote, of course, it would directly come to your cell phone or whatever the, could be tablet, iPad, whatever that you're using. So you can pause this and then just scan this code. Okay, now let's go back to this. And that is for velocity of the bat. But also remember this, there's a fast way too. You can do that, but this fast way, it is only for the bat moving towards the wall, Basha, towards the wall. What if the bat is moving away from the wall? I got Levi Baba Kati. If the bat is moving away from the wall, then this positive negative will be reversed, Basha. The one that is in the equation here, these two negatives will be reversed or opposite so that you could do the math correctly. All right, let's answer or finish these questions real quick, and then that'll be the end for this session. Section review 4.1 says, what is the relation between frequency and pitch? We said frequency, it is the number, like of vibrations, the number of waves per unit time. And we said that is from the source, which should never change. But pitch, it is, we can say the perceived or the frequency, for example, it is, or this two, actually, that's not one of the things. We also said that pitch is the frequency that is perceived by an observer, and of course that depends on the relative motion. If there is a relative motion, we could hear higher or lower frequency. And there's another way we can say that, Baba. These two are proportional to one another, but be very careful, we cannot say direct, because the book does not, actually the relation between the two is not direct. Although we can say that if the frequency of the source increases, the pitch will also increase, and that's it. But by how much, we don't know and we don't tell, Basha. The only thing you're supposed to say, these two are proportional, not direct. Basha, if we say direct, and if the frequency of the source double, the pitch must be double too. But that is not the case, Basha. For example, we've mentioned once, I believe, Gutman, for the period of a pendulum, if you remember, if you double the length, will the period be doubled? No, the period will increase by the square root of double Babylon, because there is a radical or square root relation between the two. Here, the relation is not mentioned, so we cannot say direct or it's directly proportional with the square and all of that. We'll just say these two are proportional to one another. If the frequencies increase, the pitch will also increase, and that'll be it. Sound pulses emitted by a dolphin through 20°C ocean water can travel 1,450 meters per second. But sound at the same temperature in air can only travel about bubbling 342.9 meter per second. What counts for this difference? Why in the same temperature the sound is way faster in water, but not that fast in air? That is because we know that, Gutman, the closer the particles, the faster the energy transfer, so the faster the sound will be. Kata, the answer to this question, because the water molecules are very close to one another, so it can travel way faster in liquids or water compared to air, because in air the particles are very far from one another. Basha. Question 3, Dalalo diagram Baba. Could a portion of the innermost wave front shown in this figure can be approximated by as a plane wave? Basha, when do we call these wavefronts plane wave, Gutman? If they are very, very far from the center. Aukati, once you take a portion of that, they look parallel to one another, then we can call them plane wave. Could a portion of the innermost wavefront, Basha, can we consider innermost, can it be considered as a plane wave? The answer is no, because in order to call plane wave, it has to be at great distance from the center. Okay, question 4 says, interpret graphic, Baba, says in this diagram, Doppler effect in whatever, in a ripple tank and all that. The question says, in which direction is the source of the ripple wave is moving? If you remember, when we're talking about the planes and speed of sound and all that, Gutman, whichever the object is moving, that side, kind of like push the wavefronts closer to one another. Basha, it applies a pressure on them. So because these sides are pressed here, so the object is moving to the right, Basha. Whichever the side, the wavefronts are closer to one another compared to other side, yani, this object is moving to that side here. For example, because it is moving towards this person here, you could add a person there as well. Because it is moving towards this person, Kata, this person will hear a frequency that is higher than the source, and this one, of course, is going to hear a frequency that is less than the source. That is also applicable or possible for this question here, and this one, Bin and Nuzari, related to that, says which of the figures indicate that the plane speed greater than the speed of the sound, Gutman? Oh yeah, what if it says which one of them? It indicates that the source and the observer are at rest. That would be this one here, Bashva. This one is speed of sound that is greater than the object. Here, these two are equal, and this one here, speed of the object is greater than the speed of the sound. That would be the end for this session. Till the next session, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.